we're gonna go to the next speaker. Is actually the runner-up for the Floorplan Reconstruction Challenge, Dr. Jing Dao Chen from Georgia Institute of Technology. Please go ahead. The floor is all yours. Congratulations for your success.
Okay, thank you. Hello, everyone. My name is Jingdao Chen, and on behalf of the Georgia Tech team, we would like to present our method GTS2D, and we are the second place entry in this International Scan to Bin Challenge. So first of all, I'd like to thank the organizers for putting together this challenge. It's definitely going to be a big step forward for advancing the scan to bin problem for both the computer vision and the AAC community. So first, I'd like to go over the problem again. So the task that we're given in this scan to bin challenge is the first challenge is 2D floor plan reconstruction. So we are given this 3D point cloud, this raw point cloud data, and we're given the task of reconstructing a floor plan from this point cloud. And this floor plan will require us to model the walls, doors, and stairs, as you can see in this figure. So there are a lot of challenges that are actually associated with this problem. First of all, we see a lot of variability in the point cloud data. Some have color information, some are just in grayscale. And there's also the problem of the large data size. So one of the point clouds has up to 390 million points. So processing these point cloud data is also a challenging task. And we also have the problem of occlusion and missing data. So due to furniture and other clutter in the environment, that could lead to occlusion in the point cloud data. So it's not always complete. Finally, we have the problem of noise and clutter. So sometimes the laser scanner will acquire points that are outside of the main building, and those have to be removed as part of the point cloud processing algorithm. So next, I'd like to talk about our methodology. So we did look at a lot of existing methods in the literature, and we consider kind of two main ideas in building our framework. So one is geometry-based segmentation, and the other is to use a semantic segmentation. And there are pros and cons to each type of method. So for geometry-based segmentation, the advantages are that it is quite easy to implement and it's more interpretable. Whereas for semantic segmentation, it has the advantage of being data-driven, and it can also give us detailed semantic prediction at the point level. So in the end, we decided to kind of combine both types of methods in building our framework. So this slide shows the overall framework that we use for generating the 2D floor plan. So it consists of four main steps or procedures. The first is pre-processing the point cloud data. Next, we perform semantic segmentation to predict class labels for each point. Next, we perform geometric reasoning to abstract out the walls, doors, and stairs. And finally, we draw the floor plan through abstracting lines and then projecting them to a 2D floor plan. So the first step that we perform is point cloud pre-processing, and the purpose of this step is to be able to kind of normalize the point cloud input into a standardized format that would help out the later processing stages. So under pre-processing, we have four main stages, which are downsampling, outlier removal, rotation to Manhattan layout, as well as Z-axis clipping. So the first step is basically downsampling, where we kind of reduce the size of the point cloud data, and that helps out a lot in terms of speeding up later processing. Next, we also perform outlier removal, which is used to remove points that are outside of the main part of the building. And we use two main methods, which are the connected components, as well as statistical removal based on nearest neighbors. The third step is rotation to the Manhattan layout. This is based on the assumption that most of the walls in the building will follow the Manhattan layout, where most of the building elements are aligned with the X and Y axes. So in this step, we try to solve for the angle that will maximize the top values of the X and Y axes histograms, and we'll rotate the point cloud based on this angle. The fourth step is Z-axis clipping. Here we try to find the upper and lower boundary candidates using a Z-axis histogram, and this will help us to remove points that are above the ceiling or below the floor. And this is actually important because in the floor plan reconstruction step, we would only reconstruct the floor plan for a single floor or a single story. And we'll recursively apply this algorithm until the range of z values is less than 4 meters. In some cases, the upper or lower boundary might not exist. In that case, we'll just skip this step. All right, so after we're finished with pre-processing the point cloud data, we will carry out semantic segmentation to label each point in the point cloud. And first, we actually have to do a conversion process to convert the ground truth floor plan into ground truth point level annotations. So we go through this procedure of drawing the polylines, dilating this resulting image, and finally mapping these 2D labels back into 3D. And this will actually give us the ground truth labels that are required to train a semantic segmentation model. So for semantic segmentation, we kind of just use a model that's from off the shelf, .NET++, and we use it to classify points according to the following 4 classes, which are walls, doors, stairs, as well as clutter. One of the kind of problems that we encountered was that stairs and doors were not classified well due to the class imbalance. There were many more points that were coming from walls and clutter compared to doors and stairs. So in the end, we primarily use semantic segmentation just to remove clutter from the point cloud. So the next the next set of steps go under geometric reasoning. So we actually go through this normal-based clustering step. So first we estimate the normals, the normal vector for each point in the point cloud, and we'll perform region growing based on the normal information. And we'll also do a filtering process so that we can eliminate clusters that are too small or doesn't have sufficient height. And from this information, we are able to carry out wall detection. So we basically make the assumption that walls can be modeled as a series of lines or line segments, and we use the RANSAC algorithm, random sample consensus, to be able to detect these walls. So we carry out two-fold RANSAC in order to detect both the inner as well as the outer surface of the walls. So for each wall, we also carry out a door detection procedure. So the door detection process is based on detecting openings from each wall. And we apply a histogram binning step to count the number of points in the vertical direction. And based on this, we are able to find out where the openings are located in each wall. And we also apply some minimum width and height criteria to eliminate false positives. So next, I'll talk about how we detect stairs. So this method is actually adapted from this prior method from West Bechtel et al. And here the stair detection is based on kind of a tread and riser detection step using region growing and building a 3D stairway graph, and finally generating proposals for stairway points. And these stairs can also be modeled in 2D by extracting the risers, performing outlier removal, and then detecting the lines. So this is kind of a visualization of how the stair detection is carried out. First, a series of stairway proposals are generated consisting of risers, treads, and handles. And then riser extraction can be carried out, and outliers can be removed by applying a length threshold. And finally, we can detect the lines and map them into 2D by, again, using the RANSAC algorithm and projecting the results into the 2D floor plan. And as you can see from the previous steps, there are a lot of hyperparameters that had to be tuned. These include the normal vectors, normal vector thresholds, RANSAC thresholds, minimum wall length, and height. So in our methodology, we use a grid search procedure to tune these hyperparameters. We mostly tune these parameters by measuring the performance on the validation set. And at the end, towards the later stages of the competition, we also did some minor tuning on the test server. The next few slides will show some sample results that we were able to get on the test set. So here are some results on some office buildings. In each set of figures, the left shows the input point cloud and the right shows the reconstructed floor plan. And these are some other results from office buildings as well as parking garages. So there still a lot of room for improvement in our method, and these are some ideas that we have in the future work. So we definitely like to look more into data-driven methods or learning methods to kind of improve the overall performance. In terms of semantic segmentation, we're thinking of using possibly the focal loss to handle the class imbalance, or using hard positive mining to kind of make it easier to detect classes that are occur more rarely in the data set. And eventually, we also like to look into more end-to-end learning methods into generating the 2D floor plans. So we're also open to collaboration on working on this scan to print problem or further discussion on this problem. So feel free to contact any of the members on our team, and our email addresses are listed here. This is a list of references that were used in our method, and I'm happy to answer any questions that you might have. Thank you, everyone.
Thank you so much. Thank you for the great presentation and for your participation to the challenge. I don't see any questions coming in. So for the sake of time, I think we will go on, but please, if you can stay a few more minutes with us in case anybody asks anything in the Q&A section, maybe you can answer it there. Thank you so much again for your presentation. Now we'll go to our next presenter, who is the winner of the floor plan reconstruction task. And that is Jiali Han from the Chinese Academy of Sciences.
Okay. Hello, everyone. I'm Jiali Han from the Institute of Automation of the Chinese Academy of Sciences. First of all, I'm very grateful to workshop organizers for preparing this scan to beam challenge, and I'm also very happy to get the first place in the 2D task. The method we used in 2D and 3D tasks are based on our paper, Vectorized Indoor Surface Reconstruction from 3D Point Cloud with Multi-Step 2D Optimization, which is published on ISPRS Journal of Photogrammetry and Remote Sensing 2021. In the next 15 minutes, I will share this paper with you from 4 aspects. This paper aims to convert the input point cloud into a vectorized 3D model, including the permanent structures, and our pipeline consists of 4 stages, namely scene segmentation, floor plan generation, non-wall structure reconstruction, and the wall structure reconstruction. The core idea behind our method is that we decompose the 3D reconstruction problem into a sequence of 2D segment or cell assembly subproblems by means of semantic segmentation, which reduces the complexity of the reconstruction. Each subproblem is defined as a global optimization that can be solved effectively. Besides, our method does not have the Manhattan or Atlanta word assumptions. Taking the 3D shape detection and the 2D energy optimization into a uniform framework, and having the ability to address a variety of indoor scenes with different characteristics, especially including complex scenes and the floor structures. Compared with the floor plan generated in the second stage, the wall model generated in the last stage may contain a more complete structure, but it needs use ceiling and floor point clouds with relatively good quality. Therefore, on the test datasets of the 2D challenge, we project the wall model to the ground plane to generate the final floor plan for the scenes with complete ceiling and floor point clouds. Otherwise, we use the results generated in the second stage. Next, I will introduce the details of these 4 processes. Firstly, to obtain vectorized models with semantic information. We segment permanent structures, including ceilings, floors, and walls from the input data. It is noted that we can process not only laser point cloud with high precision, but also image-based MOS point cloud. For LiDAR point cloud, we mainly use normal information and other geometric information to complete the segmentation. And for MOS point cloud, we make full use of the rich images and segment the scenes by combining 2D segment network and 3D energy optimization. Since all the data of the challenge is LiDAR point cloud, we only introduce the segment of it here. Specifically, we use an easy method to achieve this goal. First, we segment vertical and horizontal point cloud according to the normal information and compute the average height of the vertical point cloud and segment the ceiling and floor from horizontal point cloud according to this height. Then we fit the ceiling plane from the ceiling point cloud using RANSEC and obtain its height. Finally, we filter out clutter in vertical point cloud according to this height and obtain the wall point cloud. These are some examples of our segmentation results on the challenge dataset, Tall Office Floor 8, and a public dataset, Tanks and Temple Church. After obtaining the segment point cloud, we reconstructed the ceiling, floor, and wall models in sequence, followed by merging them to generate the final model. Based on the observations that in indoor scenes, wall structures are more difficult to recover due to their complexity, and walls are perpendicular to the ground in most scenes. We projected the vertical walls onto the ground plane and focused on the floor plan generation in 2D space. This stage have two core steps. The first step is the wall candidate segmentation generation. We first detect the planes attached with a set of 3D sporting points from wall point clouds and project the planes onto the ground to form the wall segments. Then we extend segments and intersect them into more shorter segments and refine them to generate the wall candidates. In the next step, we aim to select the proper segments from candidates to obtain the 2D floor plan via a global energy optimization approach. See concretely, we introduce an integer variable xi to the candidates with the mean that xi equals 1 represents that the candidate is selected. Otherwise, it is not selected. Then we define an energy function E consisting of 3 terms, S, C, and M. The S is the point sporting term. It could measure how reliable a wall candidate segment that it is selected, and the higher the spot is, the more likely the candidate is to be in the solution. The C is the point coverage term. It is introduced to balance the data completeness. The M is the model complexity term. This term is added to generate the floor plan with appropriate complexity. Then, considering that 2 rooms may be divided by 1 wall, we discard the 2 manifold constraint and restrict the floor plan to be closed, such as the conditions A to E. Finally, we minimize the energy E by means of the SCIP solver and select the candidates with value 1 to obtain the 2D floor plan. For the scenes where the wall point cloud is relatively complete, the floor plan here is enough. But if there are many missing areas in the wall point cloud, especially in MOS data, the results here may not be ideal. For these scenes, we hope to use the ceiling and floor point clouds to help the generation of the wall model and obtain the complete 3D results. Then we can project the wall model onto the ground to generate a better floor plan. The third stage is non-wall structure reconstruction, and we convert this problem into a multi-label energy optimization. First, we detect the ceiling and floor plans from point cloud and project the intersection lines onto the floor plan to construct the 2D arrangement. At this point, the obtained 2D arrangement contains more complete contours of ceilings and floors, which could help their reconstruction. Then, for recovering ceiling structures, we define an energy function on arrangement cells and minimize it to give each cell a ceiling plan label. The energy function includes two terms. The data term could measure the fitting degree of point set in each cell to a plan, and the smallest term penalized the different label assignments of adjacent cells. By using the graph cut algorithm, we could get the ceiling label results, and in the same way, the floor labeling could be obtained. In view that most of the indoor scenes have closed structures, each area in the scenes should have both ceiling and floor. However, there may be some missing areas in segmented point cloud, and the ceiling and floor label assignments are obtained individually. Therefore, for some cells and in the 2D arrangement, there may be only the ceiling or only the floor, as the right picture shows. These inconsistent results lead to an opening structures, which not only conflict with the closure of the indoor scenes, but also increase the uncertainty of the subsequent wall reconstruction. To this end, we use a label consistent adjustment step to obtain the consistent label assignments. There are totally 4 kinds of results for the ceiling and floor labeling of a cell, and only the B and C are accepted. Thus, we define a total energy E of cells in the arrangement. For each cell with inconsistent labels, such as the condition D and E, we change the cell label and select one with the minimum E as the new label of the cell. This adjustment is performed in sequence, and finally, we could obtain the consistent label assignments. Then, by lifting each cell to corresponding planes, we get the ceiling and the floor reconstruction. In our pipeline, the last stage is the wall reconstruction. As shown in the pictures, not all walls are connected from a floor to a ceiling, and thus it is not feasible to recover the wall model by simply lifting the obtained floor plan. According to the ceiling and floor labels of the adjacent cells connected by an edge, there are 5 valid height conditions as seen in B to F. In conditions that the ceiling or floor label planes of the adjacent ceilings are not connected, such as C, D, and E, and in conditions that the edge is on the boundary, such as F, the height difference marked with black is introduced. These height differences are recovered for the model closer, and whether to recover others marked with red dashed lines are unsure. As shown in right pictures, the orange walls are that with valid height difference, and the blues are uncertain walls. For solve the uncertain selection, we define an energy function on these walls, considering the number of sporting points and their coverage on walls, and minimize the function gives the final wall model results. Finally, we could obtain the complete 3D model by just measuring different parts. Next, we show some results on the test dataset. Different color means different walls. By the way, we show our results on 3D tasks. This is the floor, the wall, the ceiling, and the merged model. The wall, floor, wall, ceiling, and the merged model. Although our method could recover the 2D floor plan and the whole scene model with good quality, there's still much room for improvement. As seen in the evaluation in 2D task, the precision and the recall are low and the IOU is not particularly high. After the analysis, we think that's because we don't specially identify the doors, windows, and steps in floor plan and treat them all as walls. Besides, some small structures are not easy to reconstruct accurately due to the point cloud may be sparse here, and the missing areas and the noisy in point cloud could also reduce the model quality. Thus, in the future, we will focus on the fine-grained reconstruction and enhance the robustness of our method with the help of images or deep learning network. The above is all my sharing. Thank you for listening.
Thank you very much for the great presentation. We actually have a question, but I will remind in the meantime to the audience that you can either raise your hand or ask questions in the Q&A interface of Zoom. So the question is, what kind of tools you use to do the graph cut optimization? How long does it take?
Okay. We convert our labeling problem into the MRF problem, which could be solved by a graph cut algorithm. There are many open source tools could achieve this goals, and in our pipeline we use the alphabet swap algorithms to achieve the MRF optimization. And actually the time consumed is small, and the mainly time consumption in our pipeline may be the ceiling and the floor reconstruction. Yeah, actually the graph cut optimization time is acceptable. Thank you.
Thank you so much for your question. We'll be now going to our next presenter. Thank you again for presenting your method. And just stay a little bit more with us if you can, in case there are more Q&A questions for you to answer in the interface of Zoom. Thank you so much.